Hello class, this is a mini lecture that I'm posting. This is information that we went over in class together on the board and the small PowerPoint that's posted. But I wanted to go over this stuff again in a recorded lecture because there was some confusion and I felt like there really wasn't enough time to properly answer the questions that were asked. And I wanted to make sure that everyone was clear on these concepts since it's important to know for the exam. Now, it's important to make sure that you're familiar with the concepts of the electrostatic force and the chemical force. So these things that are responsible for generating what we call the equilibrium potential across a semi-permeable membrane when ionic species are involved. And so whenever you have molecules that have some kind of electrical charge to them, they're going to obey not only the laws that you would expect from diffusion, but also from the electrostatic force as well, which, as we'll see, creates a difference in charge across the membrane, or as we already know. And these graphs here that I'm showing, these figures are from the book. They're figure 2.8, and they demonstrate some of the data, some of the experiments that were done about half a century ago by Hodgkin and Katz when they were investigating using the giant squid axon to investigate what they hypothesized were the ions that were responsible for the membrane potential in the neuron, which we know is dynamic because it goes from a specific potential when it's resting, the resting membrane potential, to a very different potential when it is transmitting information, when it's in action, the action potential. And so they did some investigations to figure out what ions are involved in this dynamic change in potential. But before we get into their experiment, I want to first just go over how membrane potentials can be formed, and specifically in the context of sodium and potassium, which are the key players in generating the membrane potential, both the resting and the action potentials of a neuron. And so, like I said, it's good to familiarize yourself, go back in your notes in the book, go over, make sure that you're fully familiar with diffusion and chemical and electrostatic force, and then also the Nernst and Goldman equation too, which we'll be using here. This isn't a substitute for studying the Goldman and Nernst equation, even though we'll be using it. You shouldn't use just this to study those equations because it won't be complete in this little video. So let's start here with this our little make-believe hypothetical in vitro study where we've created an artificial semi-permeable membrane, which is our black dotted line down the middle of our vessel here, which we have filled up both sides with a different concentration of a salt solution, or two different salt solutions that are composed of three different species that have an electrical charge: potassium, sodium, which are both positive, and chloride, which is negative. And the concentrations are different on the left side, or what we're calling the inside. This is representing the inside of our neuron. 10 millimolar of potassium chloride and 1 millimolar of sodium chloride. And on the outside, very different concentrations of both of these salt solutions. Only 1 millimolar of potassium chloride on the outside and 10 millimolar of sodium chloride on the outside. Now, while these concentrations aren't the same concentrations that we find in our own cells and the extracellular space around them, they are similar in that we have much more potassium on the inside of our cell, and we have much more sodium on the outside of our cell, which is represented here. And it's, as you might notice, color-coded. And so in this experiment, we've made our membrane semi-permeable, so that means it's not permeable to everything, but it's just permeable to are potassium. So only potassium goes through. Now, if potassium was going through and was driven only by the chemical force, it would eventually reach equilibrium where you would have equal numbers of potassium on each side. And that in of itself would still generate a potential because these positive potassiums are moving over and there's no negative charge moving from right to left that would counteract that. There's no negative charge coming along with the potassium to counteract their additional plus charge. But the electrostatic charge actually pushes back a little bit once it starts to get too heavy, too concentrated in potassium, because the potassium doesn't like to be where it's positive. So it'll eventually reach an equilibrium. And you might remember that that equilibrium is called the equilibrium potential. Right? And this equilibrium potential, as we'll see, depends on which specific ion is permeable and the starting concentrations on either side. And we can answer exactly what that potential will be by our Goldman equation, which is sort of the a more, you can think of the Nernst equation as a simplified Goldman's equation. It can be derived from the Goldman's equation. So we're starting with the Goldman equation here because we have our three different ions. And so 58 is our constant here. That's the constant when we're doing this experiments at room temperature. That constant goes up a little bit when you are doing something in vivo, when you're doing it inside of an organism at their body temperature. And so for mammals, that constant goes up from 58 to 61. And that's because chemical reactions tend to increase at higher temperatures. Now, to get the potential, which its units are millivolts, it takes into consideration not only the concentrations of all of the ions here, but their relative permeability, which is represented by P. And the relative part just means it's not like an absolute permeability score. It's just whichever ion is the most permeable gets a value of 1. And then everything else is measured in terms of the relative permeability compared to the one that's the most permeable. So if sodium is half as permeable as potassium, the p-value would be 0.5 and potassium would be 1. Now, going back to our little experiment here, I said before that this is semi-permeable only to potassium. So what does that mean about chloride and sodium? Well, that means that their value for P is 0 because they have no permeability. So 0 times the concentration is 0. Doesn't matter what the concentration is. If the ions can't move across the membrane, they don't contribute to the membrane potential. And if you add 0 to 0 and then add that to the concentrations of potassium, you just get the concentrations of potassium. So with P equal to 0, all of these kind of don't matter. They reduce to 0, so you don't even need them in the equation anymore since their permeability is 0. So this is quite simple. And all of a sudden we see here, we have the Nernst equation right before us. So what is this for our experiment? Well, let's familiarize ourselves with the potassium again. Outside the potassium concentration is 1 millimolar, and on the inside it's 10 millimolar. So we simply plug those in. So our membrane potential is 58 times the log of, remember the outside was 1 millimolar, and the inside was 10 millimolar. So this is 1/10, or just to go through the motions and make sure it's crystal clear, this is the log of 0.1, or 1/10. And so this equals 58. You can do the, if you sort of got your log base 10 tables kind of memorized, this is relatively easy, at least with the numbers we're working with, the concentrations, or grab a scientific calculator. But you'll discover that the log of 0.1 equals -1. So 58 times -1 equals -58, and our units are millivolts. So if we were to measure this with a little electrode on either side, hooked up to a little machine that could tell us the difference in the electrical charge from the inside to the outside, it would show up as -58 millivolts. Now, let's do this again, only this time, instead of potassium, we're going to make our membrane permeable just to sodium. So which way is sodium going to move? If we open this up, shut it down to potassium, we restart the experiment, new solutions on each side, new semi-permeable membrane that's only permeable to sodium. Well, there's a lot more sodium on the outside than the inside, so according to the laws of the chemical force in diffusion, sodium's going to move from outside to inside. Eventually, it's going to reach a potential equilibrium, where the forces pushing sodium to the inside, the diffusion force or the chemical force, and the force pushing sodium from the inside to the outside, which is the electrostatic force, equal. And we're once again going to get a difference in charge from left to right because we have unequal amounts of positive and negative charges on each side. So let's do that for sodium. Again, this reduces to the Nernst equation because in our experiment, we've made chloride isn't permeable, so it reduces to 0. Potassium is not permeable, so it reduces to 0. And we've got a very similar equation that we did before. So the membrane potential now equals 58, once again, log of our concentration of sodium on the outside, which is where it was its highest, started at 10, right? And on the inside was 1. So this is 58 times the log, the log of, let me make sure that this is crystal clear. The log of 10. The log of 10 equals 1. So that's 58 times 1, which equals 58 millivolts. Just the opposite of potassium. It's not -58, now it's positive 58. Now, knowing this, when they started their experiments, Hodgkins and Katz, they noticed that, interestingly, the potassium equation, when looking at potassium, that potential, that equilibrium potential of potassium was really close to the actual measured potential, membrane potential of the neuron, the resting membrane potential. So they suspected that potassium might be responsible for the resting membrane potential. So they thought, well, hey, since the membrane is already really close to potassium's, what we would expect, if potassium were permeable, maybe that's what's causing it. Maybe potassium is permeable and is the most permeable across this squid axon membrane. And so a way to test that is to change the concentration of potassium. And they change the concentration of potassium on the outside in the extracellular space. Now what happens? Well, we can take a look here, going back to our first example, thinking about, of course, potassium is going to flow over from inside to outside because there's more potassium on the inside. What if I were to add more potassium to the outside here? You're not going to get as strong of a chemical force pushing it from the inside to the outside. And by changing that concentration, you're going to reduce that membrane potential. It's not going to be negative 58, but it's going to go towards 0. It won't be as strong. You can do this. You can do the math. Go to that Goldman equation, which reduces to the Nernst equation, and instead of 1 over 10, do 2 over 10, or you could equal it 10, which is a log of 1, and do that, and you'll find that if you do it, log of 1 is 0, and you've reached 0 for your potential. So they did this, and this is what they expected. Like, well, if potassium's driving it, and we increase potassium on the outside, that should reduce that potential, that equilibrium force, that equilibrium potential, because there isn't as much of a chemical drive pushing it over. And plus the electrostatic drive is stronger pushing it the other way. And this is what they found. Looking at the top graph here, this is simply time, and across 10 minutes, they just added different concentrations of potassium to the outside cellular space, slowly going up. Now, don't get confused by these concentrations in the example that I showed. That was just our little in vitro tabletop experiment. And those concentrations, like I said before, do not reflect the actual concentrations we see in our own neurons and in our cell. And that's why these concentrations are going much higher, because we have a lot more potassium than just 10 micromolars on the inside of our cells. So the membrane potential is becoming shallower and shallower as we add more and more potassium to the outside, because there isn't as great of a force pushing potassium to move to the outside because there's already potassium there. And by doing that, by having less of that positive charge change places from the inside to the outside, you're just creating a weaker potential. And you can see it approaching 0. You could theoretically, as they do here a little bit, start to push potassium the other way. If you increase potassium so much on the outside, some of that outside potassium is going to want to start to flow in across the semi-permeable membrane, which is the opposite of what happens typically. This figure down here at the bottom, we've traded the x-axis for concentration of potassium to the outside, and the resting membrane potential on the y-axis, which is the same again. And what they saw doing this, and make note that the scale here is logarithmic. This is an increase of 3 millimolar, and then an increase of 5, and then an increase of 10, and then an increase of 30. So an equal spacing here but each one is more and more and more, so that we can see a linear relationship with what they predicted about the slope. And so as they increase the concentration on the outside, we see a curve here that approaches a straight linear line with a slope of 58. And that number should look familiar to you because it is the constant in our Goldman and Nernst equations, 58, which is what we would expect if potassium were driving this, increasing the concentration of potassium every 10-fold should give us an increase of 58, because every log 10-fold gives us an increase of 1 when you log it. So the log of 0, or the log of 1 is 0. The log of 10 is 1. the log of 100 is 2. Right? And so this is why, and then, right, 0 times 58 is 0. 1 times 58 is 58. 2 times 58 is 116. And so that's where the slope comes from, of 58, which is what you would expect. Now, the fact that it is not completely linear, but we do have a curve, especially when concentrations of potassium are low, suggests that potassium is not the only ion that is contributing to the resting membrane potential. But because it's really close, especially at high concentrations, suggests that it's the primary one, that it's contributing the most to the resting membrane potential. Now let's take a look here. We've gone over this and our potassium and taking a look at sodium. They did a similar experiment. They suspected that moving on from the resting membrane potential, they saw that when you give it an electrical depolarizing charge, they saw a huge influx, a huge change that goes well beyond the depolarizing charge they gave it, to a new potential, a positive potential that they labeled the action potential because it was so short-lived. And they suspected that sodium was the ion that was responsible for the membrane potential during the action potential. And that's a key. Make sure that you don't get messed up with membrane potential only meaning resting membrane potential. Membrane potential is just the difference in charge across the membrane. The resting membrane potential is that potential when the neuron is not active. And the action potential is the membrane potential during an action potential, during that excited state. Now, how could they experimentally test whether or not sodium is responsible? Well, they could remove sodium from the outside cellular space, and if sodium were responsible, they would expect that membrane potential during the action potential to become less intense. And that's exactly what they saw. So this is our normal, unmanipulated, reducing sodium on the outside of the cell reduces the action potential. Now, it was asked in class about, I thought action potentials were all or nothing, and that you couldn't have like stronger or weaker action potentials. And that is the case in like an endogenous, unmanipulated, normal action potential environment, because the concentrations of sodium and potassium and the other ions involved aren't changing. You're not getting these drastically low or drastically high concentrations. If you did in a living system and you changed it that much to be able to change the action potential to be really intense or really low, you'd have to change the internal chemistry of the whole organism so much that they would no longer be alive. So you have to create an artificial environment that you would never really see exist in order to see the action potential actually change. So in its natural habitat, so to speak, the action potential is all or nothing. There's no way to sort of naturally get a more intense action potential or a lower action potential beyond special cases of some kind of, like severe pathology or something like that would drastically change ion balances within an organism, which you deviate a little bit beyond homeostasis and the organism isn't going to live. But you can sort of make the action potential more intense or less intense by manipulating the sodium, which Hodgkins and Katz did in their experiments. And then when they replenish the sodium, they're like, okay, we'll put the sodium back. And once again, the action potentials looked normal as they did before, which is a classic sort of paradigm in manipulative experiments. You suspect that there's a causal relationship between A and B. You remove A and B should change. And then if you replace B artificially, right, exogenously, then B should come back. It should recover, which is exactly what happened here. And they also discovered, and this is an important graph to take a look at here too, because I was sort of the question was asked, can the action potential go higher than what you see in the cells? And in class, I was sort of trying to figure out I was sort of trying to give an educated guess of whether it would, and I said I don't think it would because of the nature of the sodium channels and how they close at specific potentials. But clearly in this experiment, that isn't the case. As they increase the outside sodium concentration, here as we go up, we can see that the action potential amplitude going much higher beyond what we see naturally here at about positive 40. And so it goes much, much higher. They can get it by manipulating and making the sodium concentrations just outrageously high in the extracellular space. They can get this action potential very, very big. And again, it's approaching this 58 linear slope, or this linear line with a slope of 58, which mirrors our constant, suggesting that it's primarily sodium that is driving the potential during an action potential. The fact that it's curved, especially at lower concentration of sodium, suggests that there are other ions that are in play that affect it a little bit, but sodium's clearly driving it here. And this graph down here just shows they repeated the experiment they did with potassium. Let's just see if sodium does anything. So they're not depolarizing the neuron. They're not inducing an action potential. They increase sodium on the outside many, many times more than what's natural, and yet nothing happens to the resting membrane potential. It just that maybe a little bit of it depolarizes, just looks like maybe just like a few millivolts, but not at all. This suggests that the membrane at resting is all but completely locked down to sodium. Sodium can't get through the membrane. And we know from our little benchtop experiments and fooling around with the Goldman equation, if sodium can't get through, it doesn't contribute to the membrane potential, which is what we see. At rest, sodium is not contributing to the membrane potential. During an action potential, though, sodium seems to be driving the membrane potential. And at rest, potassium kind of has the opposite role. Potassium is driving the resting membrane potential. You change that, you change the resting membrane potential. So the take-home message with these graphs demonstrating the experiments that were done that led us to discover that the resting membrane potential of a neuron is due primarily to the membrane's permeability to potassium, which is much highly more concentrated on the inside of a neuron. And the membrane potential during an action potential is driven by high concentrations of sodium on the outside being permeable to the membrane. And so this is very interesting, as we'll see in later lectures after our exam, just how this happens. So this membrane must be very dynamic, right? Because we know these membrane potentials are created by semi-permeable membranes, but it's like switching back and forth between potassium and sodium, and thus giving us two very different membrane potentials, one at rest and one during action. And so what's happening with this membrane? What could be going on that makes it highly permeable to potassium, and then in a split second, it's highly permeable to sodium? So we'll find out soon enough if you don't already know or have read further in the book, or remember from vertebrate physiology, which we did go over at least superficially. So happy studying. Please give me an email if you have any questions. I'd be happy to address them. There's still lots of time. The rest of today, Sunday, Monday, I'll be checking my email regularly for any questions that anyone has.